law is also satisfied. The ninth condition is associative distributive law for multiplication, scalar multiplication. Alpha beta into u, that is equal to alpha beta ab, that can be expressed as alpha beta a b raised to alpha beta, that can be written as alpha beta a b raised to beta raised to alpha, that can be expressed as alpha into beta a raised to b raised to beta. So that can be expressed as alpha into beta u. So similarly we can prove that in bracket alpha beta outside the bracket u, that is equal to beta in bracket alpha into u. So these 9 conditions are satisfied, and the last one is 1 be the unit element of R. Then for every u belongs to V, 1 into u, that is equal to 1 into AB, that is equal to 1 into A, b raised to 1, that is equal to AB, that is equal to u. Thus all the 10 exams are satisfied by the elements of V. Hence V is equal to xy, where xy belongs to R, where y greater than 0 is a vector space. So this question is complete. The next question, question 3b. Define basis of a vector space. Let V1 is equal to 1 0 0, V2 is equal to 2 2 0, and V3 is equal to 3 3 3. Show that the set S, which contains V1 V2 V3, is the basis for R3. So here we want to prove that these 3 vectors V1 V2 and V3 are the basis vector for R3. So there is one shortcut to prove that the given 3 vectors are basis, and for that we have to use one important theorem. A set S is called a basis for V. First of all we define the basis, right? So a set S is called a basis for V if S is linearly independent and S spans V, right? S is linearly independent and S spans V. So if these 2 conditions are satisfied, then we can say that the given 3 vectors are basis vectors for R3. And for that, here is one important theorem which we use. What the theorem says, just try to understand. Here we use one theorem that if dimension of V is equal to n and S contains exactly n elements, then S is a basis for V if and only if S is linearly independent or S spans V. That means what? To prove that 3 vectors are basis vectors, we only need to prove one of the conditions. Either we prove linearly independent or we prove span, right? Or we prove S spans V. This situation happen here because what is our V? V is R3, and we know that in general dimension of Rn is equal to n. Okay, so the dimension of R3, that is also 3. Okay, and we have exactly 3 vectors V1 V2 V3. We have exactly 3 vectors V1 V2 V3. So that's why here we only need to prove linearly independent for these 3 vectors, and for that we use determinant. Okay, because same situation happen here. Dimension of R3 is equal to 3. Okay, and S contains exactly 3 vectors. So using this theorem we only need to prove either we prove linearly independent or span. But it's easy to prove for linearly independent, easy to check that the given 3 vectors are linearly independent or not using the determinant method. 1 0 0, the first vector is 1 0 0, the second vector is 2 2 0, and the third vector is 3 3 3. So that's why we use the determinant of these 3 vectors 1 0 0, 2 2 0 and 3 3 3. You can easily try to understand that the determinant of this 3 vector is equal to 6, which is not equal to 0. So hence S is linearly independent. Okay, if if suppose the value of this determinant is equal to 0, then we can say that the given three vectors are not linearly independent, it's linearly dependent, right? But here the determinant of these three vectors is non-zero element we get, so that's why it's linearly independent, and hence we can write down that S is a basis for R3. Okay, so it's quite easy to solve this example using this theorem. Okay, otherwise we have to check the second condition. By the definition, if we want to prove that the given set is a basis vector, given three vectors are basis vector, or given set S is a basis for vector space R3, then by definition we have to prove two conditions, but using this important theorem, just proving the one condition or checking the one condition, we can easily write down that the given set is a basis for vector space V, right, which is R3. So here they complete this solution of this question. Next question. Question 3C. Define inner product space. Define inner product space. Let U is equal to U1 U2, V is equal to V1 V2 belongs to R2. Define UV, which is defined as 4 U1 V1 plus U2 V1 plus U1 V2 plus 4 U2 V2. Prove that R2 comma with this inner product sign is an inner product space. Definition: a real vector space together with an inner product defined on it is called inner product space. Okay, so if these four conditions are satisfied, which four conditions? That inner product UV, that is equal to inner product VU, that is the first condition. Then inner product U plus VW, that is equal to inner product UW plus inner product VW. Then inner product alpha into U comma V, where alpha is any scalar that can be expressed as alpha into UV. And the last one is if inner product U with U is always greater or equal to 0. If inner product U with U is equal to 0, then must be 0 vector. Okay, so if these four conditions are satisfied, then we can say that the given set is a inner product space. So let's check one by one each conditions. Inner product UV, that is equal to 4 U1 V1 plus U2 V1 plus U1 V2 plus 4 U2 V2, that is equal to 4 V1 U1 plus V1 U2 plus V2 U1 plus 4 V2 U2. Okay, so because of commutative property in real numbers already we have, so we use this property. Then 4 V1 U1 plus V2 U2, V2 U1 plus V1 U2 plus 4 U2 V2, right, and that is equal to inner product VU. So easily we can check that inner product UV, that is equal to inner product VU. Here is the second condition, U plus V W, that is equal to 4 into U1 plus V1 to W1 plus U2 plus V2 into W1 plus U1 plus V1 to W2 plus 4 into U2 plus V2 into W2. So just we use the definition of inner products which we defined in this definition. You can see the inner product UV, how we define 4 U1 V1 plus U2 V1 plus U1 V2 plus 4 U2 V2. So just define in this manner. Okay, because of we have here U plus V and W, so we know that U plus V is U1 plus V1, U2 plus V2 and U3 plus V3, U1 plus V1 and U2 plus V2. Okay, so just we use that definition, 4 into U1 plus V1 into W1 plus U2 plus V2 into W1 plus U1 plus V1 into W2 plus 4 into U2 plus V2 W2. So that can be expressed as 4 U1 W1 plus 4 V1 W1 plus U2 W1 plus V2 W1 plus U1 W2 plus V1 W2 plus 4 U2 W2 plus 4 V2 W2. Okay, and some of the terms can be written in this manner. In the first bracket we can write 4 U1 W1 plus U2 W1 plus U1 W2 plus 4 U2 W2. Okay, plus 4 V1 W1 plus V2 W1 plus V1 W2 plus 4 V2 W2. That can be expressed as UW plus VW. Okay, so easily we can check that U plus V inner product U plus VW, that is equal to inner product UW plus inner product VW. The next condition is alpha into UV, that can be expressed as 4 into alpha U1 into V1 plus alpha U2 into V1 plus alpha U1 into V2 plus alpha into 4 into alpha U2 into V2. That can be expressed as alpha will be common from all the step. So alpha into we can express in this manner, alpha into 4 U1 V1 plus U2 V2 V1 plus U1 V2 plus U2 V2. Okay, and that is equal to alpha into UV. Okay, the next is 4 inner product U with U, that is equal to 4 U1 square plus U2 U1 plus U1 V2 plus 4 U2 square, that is equal to 4 U1 square plus 2 U1 U2 plus 4 U2 square. Okay, so that can be expressed as U1 square plus 2 U1 U2 plus U2 square plus 3 U1 square plus 3 U2 square. So U1 plus U1 square plus U2 square whole square plus 3 U1 square plus 3 U2 square, that is always greater or equal to 0 clearly. And if inner product U with U is equal to 0, we can easily prove that U1 is equal to 0 and U2 is equal to 0. Okay, so U is equal to 0 vector. Thus all the 4 exams, all the 4 conditions are satisfied. Hence the given formula for inner product UV define an inner product on R2, and hence R2 is an inner product space. Next condition, next question, question 4a. Check whether the following transformation are linear or not. First example, T from V to R, where V is any vector space, inner product space, and T of U, that is equal to norm U. How we define T of U? T of U is equal to norm U. Okay, so and the second one is T from set of n cross n matrix to set of n cross m matrix, where T of A is equal to A transpose. So we check that the given 2 examples are linear transformation or just not a linear transformation. So first one is not a linear transformation, that is my answer. First one is not a linear transform, and to prove that the given example is not a linear transformation, that we have to using counter example. Okay, so just T of U is equal to norm U, right? First of all, try to understand that what is the condition to become a linear transformation. The first one is T of U plus V, that is equal to T of U plus T of V. That is the first condition which we satisfied for all UV belongs to V. If T of alpha into U, where alpha is any scalar, then T into alpha U, T of alpha U, that is equal to alpha into T of U. So if these 2 conditions are satisfied, then we can say that the given transformation is a linear transformation, right? But the first one is not a linear transformation, and for that I will give you one simple example. That just see, let U is equal to 1 0 and V is equal to 0 1. Hence using the Euclidean inner product, U plus V is equal to 1 1 by the definition of addition. Using Euclidean inner product, what is norm U? That is under root 1 square plus 0 square, that is 1. What is norm V? Under root 0 square plus 1 square, that is also 1. Now what is norm U plus V? Under root 1 square plus 1 square, that is under root 2. So norm u plus v, that is not equal to norm u plus norm v. Okay, clearly, because norm u plus v, that is equal to under root 2, and norm u plus norm v, that is 2. Okay, so root 2 is not equal to 2, that is clear. So d of u plus v is not equal to d of u plus d of v. So the first condition for the linear transformation is drop here. So that's why we can say that the given transformation is not a linear transformation, right? The next one, let AB belongs to the set of n cross n matrix, then T of A plus B, that is equal to A plus B transpose. Now using the property of transpose, we can write down A transpose plus B transpose. A plus B transpose, that can be expressed as A transpose plus B transpose, that is equal to T of A plus T of B. Now T of K into A, that is equal to K of K into A transpose, that is equal to K A transpose, that is equal to K to T of A. So hence the first one is not a linear transformation and the second one is a linear transformation, right? Because of it satisfied both of the conditions. T of A plus B, that is not equal to T of A plus T of B, and T of K into A, that is equal to K into T of A. So next question, question 4b. The T from R2 to R2 defined by, in this manner, T of x1 x2, that is equal to x1 minus 2x2 and minus x2, and B is equal to E1 E2 and B is equal to 2 1 minus 3 4. Then using transformation T, standard matrix T with respect to the basis B dash, that is equal to P inverse standard matrix T with respect to the basis B into P. Find standard matrix of T with respect to the basis B, where P is the transition matrix from B to B. Okay, so since B is the standard basis, we can directly write the matrix of transformation, right? Because of B is a standard basis E1 and E2, where E1 is 1 0 and E2 is 0 1, that we all know for the standard basis of R2. So B is the standard basis, we can directly write the matrix of transformation with respect to the basis B, that is equal to, you can see in this the coefficient of x1, in the first coordinate the coefficient of x1 is 1, in the second coordinate the coefficient of x1 is 0. So that's why